Okay, ready to go? Again, for people online, I'm really unhappy with the attendance in the class, right? So maybe I forgot to make an announcement, and which means that people online didn't watch the previous lecture. But it's literal, and I will make one today. But it might be the last live stream of the semester, unless we have, let's say, half of the class in the room, right? And I appreciate, again, I mostly see undergrads here, which is great. And I believe that you guys will benefit more and learn more by being here, right? But we'll change it, right? There will be no live streams. Okay, cool. So I will record the lectures and I will post them at the end of the quarter for review. And if I made arrangements or agreed to arrangements with individual people who asked for accommodations, said, okay, I cannot come. And for those people, I will release them immediately, right? But which is fair, right? So I promised, like, I had like one or two people whom I promised, okay, I cannot do that, I cannot come. So sure. Everyone else should probably show up and instead of sleeping. Good. So today, the lecture is a little bit intense. Why? So we will go through a fair amount of low-level details. Why is that? Because in the next homework, I will ask you to build something, very similar functions, which I will cover in this lecture. The functions will be essentially mapping the page table, right? So we're mapping memory and allocating pages for the page table and mapping individual pages and regions of memory, right? And that's what I will ask you to do. Why do we need to do that? Essentially, when we want to create a new process and load an ELF binary from disk into memory, we need to allocate memory for the process, right? So this is essentially what we're gonna learn today. So last time we stopped here. So we stopped saying, okay, we're gonna build a kernel memory allocator. So what does it mean? So you can design a kernel in different ways. And this is how x86 is designed. So x86 says, okay, we're not going to build a general memory allocator, which can allocate like 8 bytes, 16 bytes, any size of memory, right? They said, okay, we're going to have a very simple allocator, which allocates just a page of memory, one size, 4096 bytes. And that's turns out to be sufficient. So if I ask you a question, so how do they allocate, for example, something like a struct proc, a data structure, which is not very big, which describes a process? They make the following approach. They said, okay, we can either allocate a page and waste the whole page, but that's a little wasteful. So instead they say, okay, we're going to have an array of max size, and that's the max number of processes we can support in a system. And they will just pick a new entry in this array, right? And when the process is deallocated, this entry is marked as free, right? Which is fine. So it's not an ideal design choice, but it's one design choice, right? And you can build the same, like in any stuff which you're implementing. You can say, okay, I fixed the maximum number of things in the system, like number of processes, number of file descriptors, other things. I think x86 allocates only one data structure, and I forgot which one. So we'll get to it, right? So that's the only one. Everything else is kind of like statically pre-allocated. Okay, cool. So our goal is to allocate pages of memory, because like literally you can't go without it, right? So you say, I want to create a new process. I need to figure out pages of memory, load the ELF text section, data section into those pages, right? And we said, okay, the allocator can be extremely simple. It can be as simple as just two functions. One allocates a page, another frees it, right? And we agreed last time that we can go with a simple data structure, which is a linked list. And this is exactly what x86 is doing. So what it does is the following. It says, okay, I will have a variable here which has a concrete name, kmem free list, And this is the pointer to the head of the list, right? So essentially, they say, okay, we're going to maintain a list of 3 pages, right? And each page, actually, it lives within the page, right? So we'll have a next pointer. And the kernel itself will have a pointer pointing to the beginning of this list, right? It's really hard to make it simpler than that. It's the simplest data structure you can imagine, right? Agree with this? So let me illustrate how it works. So for example, it's simply a struct, which they gave a name run, and it has the next pointer, right? So this yellow part here, this one in every page, yellow, 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 is this run, right? Each has just one single field, next, right? That's a linked list. And of course, you say, look, when I allocate a page, I simply pick the pointer, the head of the list, which was pointing to this page, read this next pointer, assign it to the next head, right? And I return this previous pointer to whoever called the alloc, right? Agree? Very simple. Like you probably built something like that, right, in your life already. And so on, like you say, the next page, cool, we'll get this page, right? And it's off the list at this point, right? So it's no longer on a free list, it's available. Anyone can, like, whoever allocated this page can use it, right? Similarly, you say, if I free, you get page back to the list, right? And that's kind of allows you to manage all available pages, right? Very, very simple. So if we look at the source code of this data structure, again, super simple. I skipped a couple of lines here and we'll come back like later to what's there. But literally you say, I take the head of the list, right? If it's not empty, I will assign the head to the R next. This is R, right? And R next is this one, right? Agree? Everyone built linked lists before? Like, I don't know, like in C, maybe in Python, everything is so well hidden that you don't even use a list. You always have a collection like map or something, right? Sequence. Here you say, look, okay, this is a list, right? Agree? Okay, cool, not super hard. And similarly, if you free, so you have a k-free function. Actual name of a function is not free, but k-free. K stands for kernel, but doesn't matter. You say, look, I'm given a virtual address, right? It's a matter of a design choice which type to choose, right? So they chose a pointer to a char, right? And so that's why they typecast it, because they say, look, someone gave me this pointer to this page, but I will typecast it to the pointer to this struct run, right? It's a little unusual. I mean, for people who use unsafe languages, it's fine. For people who use safe languages like Java, Python, you say, look, really, I can take one piece of memory and turn it into another. Well, turns out you can, like, because remember assembly. For assembly, it's just simply a pointer. Types are for you to not to make too many mistakes in the programs, right? Python is type safe. Good luck to you. Debug all the errors up front, right? So because it will only check the types dynamically.
Is there a reason they don't use a void pointer instead of a char?
That's what I was no, really not. I mean, I would probably go with void just to emphasize the fact that it means an address. A good operating system like FreeBSD or Linux, they will introduce an address type just to highlight for a human that this is an address. It's not a character. It's just an address. And then weight probably would be, it's about the same, right? So it's design choice. I mean, this is a deficiency in C. So like certain design choices for how to handle types are kind of maybe not ideal, right? Okay, cool. So we have this free list and we say, look, this is how we want to have our memory allocator to be working, right? There is a tiny detail here. So the design choice which x86 makes says that this run data structure sits within the page itself, which means that if you want to write something into run, it has to be mapped by the page table, right? Because in general, you cannot access physical addresses, right? Because any address which you put in a register will go through the translation the moment you enable segmentation and paging, right? So you have value 55. It first goes through paging or through segmentation, maybe the base is added, and then in our case, the base is not added because the base is 0. And then it goes through paging, hits some physical address, right? So if you really want to access a physical page, it has to be mapped by the page table, right? So do you remember how what is in the page table right now? Because you can't even like access the linked list if it's not mapped, right? So it has to be mapped. What do we have in a page table right now? Yeah, when it first bursts. It's like when you reach main. So because this, like, it's at the very beginning of main, you start initializing this memory allocator. It's very correct. So that's your map. So your page table is still this boot time page table, which uses 4 megabyte pages. And we map the same region, so this physical region from 0 to 4 MBs. We mapped it twice, at address 0 to 4 MB and at address 2 GBs, which is here, which x86 uses the constant kernel base to the 2 MBs plus 4 megabytes here, right? Okay, so which means that if we want to track physical pages, right? And imagine we want to track all physical pages, like x86 boots with 234 megabytes of memory. It's just a constant, right? So maybe the system has actually more physical memory, but x86 simplifies this design choice and says we're going to just assume that machine has 234 megabytes of memory. And we want to keep track of all of these pages, right? So sorry, like somehow my hand is misaligned here due to how the table is positioned, right? So up to this limit, right? Clearly, we cannot access these pages because like they are not in a page table. So the page is unmapped, right? So this physical page is not mapped. But which pages are mapped? Like initially we say, look, like not everything can be even accessed. We can only access 4 megabytes, right? So, and it's kind of a chicken and egg problem. We say, look, we probably will construct a page table which will map entire available physical memory. But right now we have this kind of like limited page table, which only maps this like one physical region into 2 virtual addresses. So just to bootstrap ourselves, which pages can we use? We can do tricks and different design choices.
You're saying that pretty much effectively in x86, all of the pages are pretty much statically determined prior. Yes. So
in the boot,
yeah. Map the rest of the 8 megabytes or however large your address space is.
You're saying, so one design choice is to say, I will map more 4 megabyte pages, right? So just add more entries to this page table.
Right.
That's a sound design choice. You can, right? So actually, I don't have much against it. So you can say, look, let's just add them all. Why not? Just write a simple for loop like you do in a homework and just fill them in, right? Up until this stop constant. Totally, that works. But for whatever reason, they make a different design choice. They say, look, we already mapped 4 megabytes here, right? We know that the kernel is smaller than 4 megabytes. And so this memory, which is above the kernel and up until the end of the 4th megabyte is available. So they say, look, first, let's add this memory to the list, right? And keep track only these page tables. And then we will construct a new page table which will map all available physical memory, right? That's the design choice they do. So they do it in 2 steps. I just wanted to explain it, like, but there are many design choices and yours is probably cleaner. So I would probably choose yours, right? Or I would even, if I were building it, I would probably, instead of using this 4 megabyte page table, which uses 4 megabyte pages, I would construct a page table in a way similar how I ask you to construct it in the homework. Just say, look, just give me like, let's construct a page table which covers a little bit more memory to begin with. But and it used to be that way in x86, then they changed, and like this is just like whatever. People make different design choices. They're kind of equally okay-ish, right? Question.
Can you go over the two steps? Yeah.
The two steps, which steps?
The two steps that x86 does.
Yeah, so no, hold on. I'll go very carefully. So right now we have this just 2 pages mapped. And what they do next, they say, let me just high level picture. They say, we're gonna first add these pages. Sorry, I don't know, like usually I'm like, I can do better lines, but and the lines actually, still alive? Yeah, good. Let me try to do some straight lines here like this. They say, we're gonna just make sure that we're gonna first handle those like number of pages which are available from the end of the kernel to the end of the first megabyte, because it's mapped. We can create a linked list, and we can use this small number of pages as a pool of 3 pages, and then they will do a trick later. So let's first do this. Okay, cool. They specifically say, let's take all available pages which start at the end of the kernel, which on my machine, when I compile it, ends up something like this, right? So it's roughly like 1 megabyte plus some size of the kernel, right? And the linker allows to insert a simple AND, so the C knows this AND as an address, right? And all of the pages which are above the AND can be added to the list of 3 pages, right? This idea is clear at a high level. 4 kilobytes. So, and okay, another design choice is just stick to 4 megabyte pages, right? And that's okay, especially in a modern world, but in a world of x86, each x86 process, like we've seen it, cat fits on one screen, right? So it's probably like in the order of less than kilobytes, right? If you add the printf plus some malloc libraries, maybe like 2 kilobytes. So you don't really need a lot, like waste 4 megabytes of memory just to create one process. That's why they switch to small pages, but also to illustrate the point, partially, to illustrate the point that, okay, normally you will end up working with this page table. So let's do it this way, right? Okay, cool. So this is exactly what x86 is doing. Like immediately after entering main, right? The very first function they call is called this kernel init1. And kernel init1 says, okay, we will donate free memory to the memory allocator, starting from the end symbol, going to the end of the 4th megabyte, right? So this is the chunk of memory which is currently mapped and not big enough, but good enough to make this pool, right? And what's internally, what this function is doing, it just, how do you donate something to this list? You just free the pages. You kind of pretend that they were already allocated, but if you free a page, it will automatically be added to the list, right? Because that's how we designed the free function. And so they essentially say, okay, we're gonna free range of pages from the virtual start to the virtual end. And I will reiterate one more time. So it works very, very simple. So free range. So they round up this virtual start to the next page, right? And take the pointer P and essentially increment it by the page size. Page size is 4096 byte, and it goes up to virtual end, right? So kind of, okay, so why not? And they free every page. And essentially each of those pages will get on the list of 3 pages, right? And again, this AND symbol, remember the K init1 is called with this AND symbol. And in C, you say extern char AND, saying that this symbol is defined somewhere else, but really this symbol is provided by the linker. So if you carefully read the linker script for the x86, you will see that, and that's why they use the linker. Let me show you very, very quickly again, just to make sure that we understand homeworks. We're not gonna take a look at the homeworks. This one. Let's quickly go to just, no. I just wanted to show where this and symbol kernel LD. So this is the kernel linker script. Remember, very similar to the one we use in the homework, right? So I was saying that we can tell the linker to link the kernel at like 2nd gigabyte plus 1 megabyte. So the text section is exactly at this address. And at the end of this script, they say, look, we're gonna define a symbol and after everything, BSL's data. So that's the very end of the kernel, right? And this is the way to connect the linking to C, right? So you say, look, I don't know upfront what the size of the kernel will be, right? And so I will use this linker script, and linker is so smart that it will, in the final ELF binary, it will provide a symbol end, which will be the end address of the kernel, right? And if you say extern in C, then the compiler will correctly link, like compile the code and will link correctly with this, right? Is that this trick is clear? Okay, cool. Okay, so we got the end. We got the memory on the memory allocator. So like that's just the slides which explain the same. And at this point, we have we achieved something. So we have an allocator which is initialized with some number of pages. I used to ask, I think on the exam, how many pages are on this allocator, right? Initially, it's not very hard to compute. You need to get this symbol, the end symbol from the obj dump, and just like count how many pages fit if you round it up per page. But what is that roughly? I don't know. We can count later, but maybe 100, right? So enough to start running, right? And now, again, our next goal is to say, let's construct a real page table, which is as flexible as we can get, because this boot time page table uses 4 megabyte pages. That's not okay, and it has only 2 entries. Let's construct a real page table which will cover all available physical memory, right? So, and that's exactly what x86 is doing in the very second function, which is called kernel virtual KV malloc. So it's essentially allocate a kernel virtual page table and allocate a kernel page table and initialize kernel virtual memory, right? Let's take a look what it does, right? So again, like we're in main here, right? We booted, we got the memory allocator here. Now we're executing the second function. If I ask you a question like, what do you think needs to happen in this function? Like, first of all, again, are we clear on the fact, why do we really need a new page table? What is that? What is it we want to do with it? First of all, like we know that each process will have its own page table, right? So why do we need a page table for the kernel to begin with? Who can tell me? Maybe we don't.
Each process has its own kernel.
Kind of. I mean, that's a little bit of a like, this question has many answers and many important, maybe yours is also correct. It just not specific enough, I guess. Let's hear more versions and then we'll come back.
Maybe when a process needs to switch back to the kernel, you just swap out the page table to the kernel page table.
Correct. So again, okay, so first of all, probably it's possible to construct a system which doesn't need a separate page table for the kernel. My use case, which I have in mind, again, like you ask me, okay, does it really matter? So again, let's a tiny anecdote here. So we are building a new operating system because it will be fully verified. Building those mathematical proofs which reason about the correctness of this kernel is a little hard. So the kernel is very, very simple, even simpler than x86, believe it or not. You can build a kernel which is even simpler. But pretty much what we're building is very similar to what I was covering in this last couple of lectures, you know, boot into main, initialize the page table. Now we have a design choice. Do we need a page table for the kernel? Like one student on the team says, well, no, forget about it. Because each process will have a page table, so we can always use some page table. And what do we do if all processes quit, right? At this point, like it can happen, right? So like you boot into cell or init and it immediately quits, right? In x86, it doesn't quit, but let's assume it quits. Maybe it crosses, right? So then what are you going to do at this point? There is no page table, right? One design choice to say, okay, since it's the last process, we're not going to be able to create any new processes. So just let's halt the system and never run again, right? So, and this way you can construct a system in which you don't need an extra page table for the kernel, right? But we decided to anyway to have a page table because it was a little bit easier. Like x86 did the same design choice to say, look, let's have a page table for the kernel. And then every time we construct a new process, we will construct yet another page table. And when the process quits, we will clean this page table and switch to the kernel page table, stuff like that, right? So it's a little easier in the end, right? But it's again, it's a design choice and you can make it different. Sorry, that took me a while.
Better for like
Because the kernel is what?
You're using a completely different page table, so there's less risk of like.
Right. So I mentioned the trick. So when you always switch to a different page table, and that's a trick to address the meltdown attack. So and the trick was called kernel page table isolation, KPTI, kernel page table isolation. It slows you down a lot because switching the page table is quite expensive. So, and so.
Does that require having a kernel page table? Like you wouldn't be able to.
Right, yeah, that would require a separate kernel page table. And if we are lucky and have time, I will explain the meltdown attacks. If not, I will assign them as extra credit or something. And but hopefully the CPUs will fix all the meltdown problems in hardware, and we don't need to do this trick. Another question.
Could it also help you catch bugs? Like if you have a page table and your kernel has a bug where it tries to access an unmapped page, then it will blow up on you.
Not sure. Okay, let's maybe move forward, and then I don't think it will work or will have a significant impact, but maybe it's probably what it does. It simplifies the cleanup function because when you clean a process, you say, I don't really have to reason about whether it's the last process or not in a system, and I'll just uniformly clean up. But this complexity is not that hard, right? Unless you build mathematical proofs about it, then it kind of like slows you down a little. Okay, so they say, okay, let's have a very clean, nice page table. And also, why am I like going into those details? Because those functions which build this page tables, right, and kernel address spaces will be used later when we're going to build processes, right, like with the exec or fork system call, right? So that's why it's important to like take a look at them actually multiple times. Okay, so at a high level, the goal is the following. If you have this physical memory here, which starts at address 0, x86 says, okay, since I don't want to ask BIOS about how much physical memory I really have in the system, I will just define a constant, which is fstop, which is defined in hex specifically like this, and it's roughly 234 megabytes. And again, Wacom quit on me. And yeah, really like twice a day. Let me quickly kill it and restart. Just a sec. What do I do? Just reset. Went back. It's back. So you see, I can fix all the software problems with a quick restart. Okay, so we're back here. Sorry, like my dramatic reveal was all ruined. So fstop is here, right? So this some amount of physical memory will be unused by x86 because it doesn't reason about it. It says, okay, I just like for simplicity, we'll skip. And the high level goal is to map the physical address, which is at physical memory at address 0 to the second gigabyte, right? And then map everything with the same shift. So essentially map fizstop to this location and 2 GB plus fizstop, right? And this part of the address space will be used by the kernel. And when we will be creating a new process, we will also initially create an empty part of the page table here, but as the process will be loaded, we will allocate additional pages here, right? In the user part. Okay, cool. It turns out that this physical memory also is not just like blank space, right? So there is a little bit of IO space below the kernel, right? Used by the BIOS. And remember, when you do hello world, you really write your letters. Sorry, you write your letters. Let me erase this line. You write your H and so on in this wonderful region. So this is the BIOS region. So you write H somewhere here, and it eventually ends up on a screen because the frame buffer sits here, right? Do you remember this? Okay, cool. Then we loaded the kernel, and we say, look, the kernel text and data will be read-only, and there will be a read-only data section, and there will be a read-write data section plus free kernel memory above it, right? So roughly speaking, this can be region 1 for the BIOS. This read-only kernel is region 2. Writable memory is region 3. And it turns out at some point, people ran out of BIOS space in this region, and they said, okay, there will be also another IO space region at the very end of the address space, at the very top, right? Just needed more BIOS space from new devices, right? So this address space is not just like one flat from 0 to fizstop. It has parts, right? Okay, sure. Let's map them slightly differently. We say we're going to map BIOS read-write, kernel read-only here, this region read-write, and this one is read-only as well, right? Oh, sorry, not read-only, read-write, otherwise we'll crash and we'll try to communicate with some devices, right? And when I say map, our outline will be roughly the same. We say we will start at virtual address 2 GB because we map everything with the 2 GB shift. So physical address 0 will be mapped at virtual 2 GB, and we will iterate this region page by page. And as we go forward, we say, look, we will allocate parts of the page table which are needed to map those regions, right? And fill in the entries in the page table, right? So roughly, I have like an illustration for you. You say, look, if we start from this state where we have this boot time page table, which maps these 2 regions, we say, look, we'll start by allocating page table directory, right? Because we need a root of a page table. So essentially, simply go to this like kalloc, right? The function which we just created. It will give us a page. Maybe it will be the page from here, right? Like from the beginning or from the end of this region, depending on how the list is constructed, right? But somewhere here, right? We say, look, we want to map which address we want to map first. This V, right? So V maps to this P, which is 0, right? And we say, look, since there is no page table level 2, we again go to the allocator, allocate the page for this. And after that, what we do is that we simply say, okay, we will fill in this entry to essentially to say, look, this one actually points to this, sorry, not virtual 0, but sorry, the physical 0, right? Agree with this? So it's kind of like you do in a homework, you do this loop, iterating through like whatever from 0 to 8 MB, but here I will be iterating from 0 to fizstop, right? And then we go to the next address. So like the way we fill in those flags is just simply assigned to this location in memory, right? Where the page table entry is located, which means that this page, physical page is mapped to this virtual address, right? Agree with this? And after that, we simply move to the next page. So we iterate the pointer by +4 and start going with this next page, which is next physical page, right? That's the high level plan, right? It's very easy, right? Like exactly what I asked you to do in a homework, right? Not hard. Okay, but let's take a look at how kernel does it, like actually how x86 implements those functions, right? Okay, cool. So that's the name of a function, kvmalloc, right? And here again, I will be showing you the invocation stack from the main function. So we're inside the kvmalloc. The first thing we're going to do is we say, look, we're going to use this function, set up kernel virtual memory, which will return us a pointer to the new page table, right? And the moment we're gonna it's a global variable, we will switch to this page table. Very similar to how you do in the homework by reloading the CR3 register, right? Okay, so let's first take a look at what this setup KVM is doing. So setup KVM, as I was saying, like literally, it's the high level is this loop, right? So we first allocate the page table directory, a page for the page table directory. That's why we need this allocator. Kalloc allocates us a page. If we fail, we exit immediately. The system will not boot, right? So we are careful about it. So we say, look, we allocated this. We're careful saying that if we also will set it to 0, because that's another trick, right? When you work with this memory, maybe this page was accidentally used by, I don't know what, maybe even after BIOS reset, it's not set to 0. Who knows? Maybe BIOS was using this page. Maybe Grub was using this page. Who knows? It may not be zeros. So that's why you set it to zeros, right? But after that, you say, look, this is exactly the loop. You say, I will be using a function which maps a region of memory. But remember, I said that there will be 4 different regions, like BIOS, kernel read-only, kernel read-write, stuff like that. They use a helper data structure, which is called kmap, a map of the address space. And this kmap, specifically, what it defines is those regions. So it says, okay, I will only have four entries: entry number 1, entry number 2, entry number 3, and entry number 4. And if you look at how this is done, I will show you a data structure itself, right? So it says, okay, it's a simple data structure. It has a virtual address, physical and permissions. And it really literally has only 4 entries, like from kernel base to, from 0 to extended memory, which starts here, right? And essentially with the right flag primitive. So we don't really have to spend too much time, but these 4 entries essentially encode these 4 regions, right? Okay, any questions? It's just, okay, low-level details of this code, probably not very important.
So confused. At the beginning, we have the 4 megabyte for both the beginning and the beginning and the 2 gigabyte. So now we are located these 4 kilobytes page table. Where are the previous page table pages?
Good question. So, okay, there's a couple of questions here. So let me just pick a good slide which will illustrate my point. Let me where are we? Let's say this one, right? Let me erase everything. Sorry, erase. So this entry page table, where is it allocated? Who remembers? If I on this, inside this physical memory region, this page table, where is it? If I were to like circle it.
In the kernel, we don't make it.
It's actually not read-only. I would say it's probably in a kernel BSS, right? Or a data section, right? Agree? So somewhere here, right? So this is specifically this data structure, right? Mm-hmm. Is there anything else allocated in a data section, on a stack, or on a heap for this data structure, for this mapping to exist?
Page directory.
This is the page directory. It uses, well, I call it a page table as a, sorry. So there is a little bit of a confusion with the terminology. So when I use a multi-level page table, I call the whole thing a page table. And that's why I call the whole thing page table, although this one has only one page table directory level, because it's a 4 megabyte page, right? No, you're right. So it's worth clarifying. So, but is anything else was allocated?
You probably have a pointer to it.
We have CR3.
I don't even think that, I don't think you even have a pointer, because you remember how we did it during the boot. We just loaded it into the CR3, right? So we like literally loaded the address with a move instruction. We first read the CR3 into an EAX. Oh, I forgot how it was. Yeah, I think all of those waves. right? So I think that's it. There is nothing else in this system which is allocated to support this page table, right? My goal was to, but so when you say, okay, I'm gonna allocate new page table, right? So I will allocate a page table which looks like this, multiple levels. We will be getting pages, right, from the memory allocator, which sits here, which those pages will physically sit somewhere here, right? And then eventually we will load this new page table into the CR3, right? Saying we switch to it, right? The old one we will just simply discard. So we're gonna lose this memory, which was allocated in the data section, and we'll never use it again. So which is a little wasteful. We lost 4 kilobytes of memory, but it's okay. But I don't know whether I answered your question the way you asked it, or just kind of provided you the intuition that what was allocated, right? So this is just a table which provides the mapping, but nothing else is allocated, right? So this mapping was mapping these virtual regions to this one physical region, right? Agree with this?
So where is the new page table
In memory?
inside? Yeah, is still in the kernel or?
Okay, let me show you. And
Previously,
this line allocate the root of the page table directory. So if I will end up doing something like those dashed lines are not yet allocated, right? So the leaves the page table, right? This one is allocated by this kalloc function, and that's the pointer to this root of the new page table. And the kalloc is the function which we just built. It's the function of the allocator. So it picks the page from the free list. And the free list is initialized from the end symbol to the 4th megabyte, right? At the moment. Everyone agrees on that? It's like a little bit of low-level details, but you have to keep track, because if you screw something up, then you're not going to run, you're not going to boot. With stop, right? In x86 is just a constant, right? They say why? For pedagogical reasons, because really a real kernel will query the BIOS saying, okay, because BIOS knows how much physical memory is in the system. So you have to query the BIOS. It's not super hard, but it's a little you will not be able to boot on all the systems because BIOS, it will be lengthy. Like we do it, like obviously when we boot our systems which we build, we query the BIOS about available, or we actually rely on grub, the bootloader, to query the BIOS, and then the grub provides us a specific data structure which tells us how much memory we have. So that's how it goes. But the x86, just to keep things simple, they just say, okay, fistop 234 megabytes for now. You can change it and run. Okay, good. Anything else? Okay, so does this answer your question? So those pages will be coming from the memory allocator, right? That's why we created the memory allocator, to even be able to implement this line of code, right? Because you need those pages, right? Okay, since we talked a little bit, let's do a poll quickly to warm up. I have a couple of polls for you and for people who are online. The very first question I'm asking, it's actually very, very, very related, right? So do you see a question online that I'm asking at which physical address the kernel binary is located? Do you see it? No, not active? Not active? Activate. Okay, cool. There are 2 buttons. One is called lock and one is called activate. It's a good design. So I don't know what lock is. It's active, but you cannot answer. Maybe so I can still. Okay. I'm seeing the answers. Physical address at which the kernel binary is located. So let me maybe show you a better slide. Maybe this one? No, it's the same. No, it's actually okay, maybe not this one. Let me show you. I don't even know, let me show you a good one. This one. This one is definitely good. Let's just erase everything. So you can't go wrong with this slide, right? So it shows you everything. So let's 80% of people gave the right answer, but 20 did not. So let's think about those 20. Okay, who is unclear on this? Like, okay, let's vote. Like, where is the kernel in physical memory? Which address? Anyone? Like everyone is sighing because it's obvious right now. It's not obvious with the 20% of people, believe it or not. It's like voting, you know. It's obvious for me what democracy means, but it's not obvious for everyone, right? So yeah, so 20% of people insist that it's at the second gigabyte in physical memory. So this is wrong, right? The kernel is at the very first megabyte. And the reason it's there, who can tell me? Oh, I'm sorry.
Is it just because it's reasonably above?
It's actually exactly above the IO, right? So if you write it in the IO region, good luck to you. Let's try. Depending on the bias, it will and machine, it will behave differently. It's right above the IO, and of course below the fifth stop. And remember, I forgot what was the reason we did it this way. We're in 32-bit mode, so technically speaking, you can put it anywhere from 0 to fifth stop, right? Max available memory, right? But you just assume that there are, like, if you have a real physical system and maybe it has very small amount of physical memory, like 8 megabyte, right? So let's keep it close to IO. You know that this memory should be present, most likely, right? That's the reason, okay? Right? Agree with this? Any questions? Okay, that's why we loaded there. Otherwise, I would argue to load it directly at the second gigabyte, and we'll never do this trick with remapping, right? Just map 1-to-1. Why not?
How do we know that that's exactly above? There's some.
Yeah. So yeah, there is a standard which says, okay, this is where those addresses will be located. Like for the PC machines, there is this standard. Which. Okay, I will ask you the second question, which is equally tricky. So let me deactivate this activity. I will lock it, and I will go to the next one. Like this one. Do you see it? At which virtual memory the kernel binary is located? Let's see about those 20% again. It's a good recap. Okay, we voted. And it's exactly opposite. Again, 20% of people believe, actually 24 right now, 25, believe that it's at the first megabyte. So, but everyone in the room, I hope, knows that the virtual address is actually here, right? Which is what? Which is 2 MBs plus 4, 2 GBs to plus 4 MBs, right? Agree with this? That's how we mapped it, with a 2 gigabyte shift. I just wanted to make sure that we remember this this map, because it will keep coming back. So, and like it's a design choice. You can make it different, right? But that's how x86 did it. Okay, good. We submitted the answers. Everyone did.
Uh-huh. Is the physical address at 4 megabytes?
Is the physical address, say again?
Oh, wow. Is that 4 megabytes or 1 megabyte? Where the kernel would be physically.
In physical memory, it's right here, right? This is 1 megabyte.
Well, but in the virtual address is 4, not 2 gigs plus 1.
Oh, I'm sorry. Yeah, my bad. That's 1. Right. And okay, so maybe the way I asked the kernel, maybe the way I asked the question, it's a little bit confusing, right? Because we still have double mapping. So you can kind of say that you actually kernel sits here as well, right? So, well, that's like the change in democracy again. Let me actually edit this. Actually, the correct answer should be both, right? At this specific point in time, let me mark it as both addresses are correct. So the picture should be, it actually exists at both 1 megabyte and 2 gigabytes plus 1 megabyte. Thank you for this correction. Apologize. Right? Do we agree with this? Yeah. So no, like both, like I got it. So, but you corrected the 4, and I realized that it's double mapped right now still, right? Because we're using this boot time page table.
So when you're in the process of mapping, have to be direct physical map. If you're getting them.
You mean like direct one-to-one? Or
Can't, but you don't have virtual addresses yet. Because like. for
okay,
like a
let me
little bit-
hold on. Let me. That's a good question. So what this your classmate is asking is that, like, when I'm creating a new page table, which addresses am I using? And like any versions, what is it I'm doing? I say that I'm still using the old page table because it's still loaded in CR3. The fact that I'm constructing a new one is invisible to the hardware. It just my whatever, my future. And then atomically, I will reload CR3. And the moment I reload CR3, the new page table kicks in. Up until then, I'm still using all the virtual addresses in the old one.
So how does that work with, because isn't the old one sort of like overrun memory of where the other page table was?
Good question. So, okay. So it's a question of mappings, right? So what's the natural analogy? It's kind of like, think of it as multiple views of the same physical area. So imagine we have this room and somehow I came up with virtual reality glasses, which show you like half of the room. And you say, look, this half chairs, no matter how you look at it, it's just this part of the room is available and you can sit it in, and everything else is maybe lava, right? And so you say, look, I'm gonna sit there, and I'm meanwhile constructing the new view, but I'm not showing it to you. Then you really like, you say, I know that there are chairs there, they're just not visible, but I know about it, right? I know about them. And so eventually you say, look, I can say that, you know, student X will be sitting at the chair, and then at some point I will enable this view by preloading the CR3. And those chairs suddenly become available, right? The fact that there was a different view of the same physical space is probably, it's relevant because if you right now try to access the virtual address, which is not supported by the view, you get a page fault, right? But we are careful and we are not accessing anything. So, and the pages which we are allocating from the free pool, they are so carefully, the free pool is small. It's up until the end of this 4 megabyte region, right? So which is mapped by our current view. So I'm very careful to use only those chairs right now, which are visible to you. So that's why you're not crashing into the chairs, which you don't see, right? But then eventually I will enable this view, right? Does it make sense, this analogy? So it's a good question, right? So it's a little unusual how the virtual is just a view, and it's not really like if you try to access, you crash because the mapping is not present. But if you don't, then it's fine, right? You can imagine that in the future it will become available.
I have an intuition, I guess, claiming that the end of the kernel data versus like the end of the 4 megabytes would not be like evenly visible by 4 kilobytes. Is there any way that like
Yeah, so that's what
left over after dividing?
Right. So when we enter this k init, right? Is that what you're saying? We just round up the page to the next. Where do I do this? It's when we were allocating the memory allocator. So here I said round up to the next page, right? So if this is the page and end sits exactly here, then we're not going to use this page because the kernel sits here, right, up to this end, right? So we will use the next one. Mm-hmm. That's what you were asking?
Yeah, so that's effectively still from the, I guess.
No, this space is lost, so it will never be,
not.
Yeah. No, like it's a physical page in memory. It just will never be used because there is no way to the pages are always at a page align boundary. So 496 byte boundary. So you have to skip it. Okay, good. All the questions, the views are clear, right? Let me log my activity for everyone who like still the answers are probably semi-correct, but we can keep going. So yeah, so poll, that was the poll. So kernel map. Okay, back to this loop. So loop is reasonably simple, right? So again, so they just use this helping function, which the helping function itself says, okay, map the region of memory starting from this virtual address here, like start virtual address of this specific size. So remember in the kernel map, they provide the physical start and physical end. So they just do the arithmetic to compute the size. And they say, okay, this virtual address will be mapped to this physical address, right? So reasonably easy. And those are permission flags for this region, right? And they also pass the page table directory, which we allocated right here. So it gets passed here. And this is the root of the page table on which this function operates, right? And again, what's inside this function, right? So again, we're called from main, kv alloc, setup kvm, and this is the function map pages. So we have these two arguments, virtual address, and we say virtual address plus size. So again, round up, round down to make sure that we only map whole pages, right? So not super hard. And then we say, look, we remember what we want to do. What we want to do is the following. We want to have a page table with two levels allocated. And in order to map a physical address into a virtual address, we need to essentially write into this entry, right? With this, just essentially write the address of the physical page, right? This address P here, right? And so the question like, how do we get this PTE, page table entry, right? Which is like, it's a tree, page table is a tree. We need a specific entry in a page table. So how do we do it? We have this helping function, walk page directory. What's inside that function? Because like everything, we can jump ahead a little bit. So if we have the address of this entry, right? So this is PTE in my previous slide, then simply eventually we do this right, updating the PTE with the physical address of a page, permission bits and the present bit, and just we'll go to the next page. That's our loop, right? Like I was describing it. But we need this PTE. Everything else is relatively simple. We just need the PTE. Correct. So literally what this walk page table is doing, it takes the page table as an argument. It takes the virtual address as an argument, A. It splits this virtual address into 10 bits, right? And says, okay, this first 10 will index into this page table directory, right? We'll figure out the entry. We'll walk it, similar to how the hardware walks it. We'll go to the next level, figure out this page. We'll use the next 10 bits and figure out this page table entry. And this specifically is a PTE, right? This is the pointer to the page table entry here. So, but constructing this function is not very hard. And if this second level is not yet allocated, we will allocate it as we go. We'll check for it, and if it's not allocated, we'll allocate, right? But at a high level, it's easy, right? Just kind of pretend how the hardware resolves virtual to physical and figure out this entry, right? Same algorithm. Agree? Okay.
My question is, where could we get the virtual address? My second question is, like you said, if that page table, PTE, the page table does not exist, it will also allocate from the free pages list.
Correct, right, yeah.
But where we get the virtual address?
No, remember, we are invoked with the virtual address argument. We round it up to A.
Yeah, how could we get that argument?
What do you mean, how do we?
When we call this function mappings,
yeah,
how could we figure out what's the virtual address?
No, we're using this kernel map, and kernel map says, okay, I'm defining 4 regions. First region from 0 to first megabyte, that's this region. Then from the kernel link, that's the first megabyte, to kernel data, the read-only data, because that's the end of this read-only region. This one, this is the second one. The third one starts from data and goes to FISTOP. That's this region, right? And the fourth one is this def space to to what? To 0. It's a little bit of a trickery here because 0 kind of overflows the address space back to 0, right? But that's the end of the address space. I would prefer. Do you see it? So we just by hand define those addresses statically, and that's data structure is part of the kernel. And then when we invoke this function, we just say K is an entry in a K kernel map, right? And we just say K virtual is the virtual address, and so we have it here inside the function, right?
So that means before we use the virtual memory is already reserved, right? If we use all these reserved virtual address, we could not have more.
Okay, hold on. So virtual addresses is kind of like, yeah, it's a resource, right? And we say that it's more about, again, let me use my analogy with this room. Let's imagine there is like a construction in the middle of a room and we cannot use those chairs, right? So when I create a seating for the midterm, I say skip those chairs, because if I assign students to sit in those chairs which are not present, well, we have to somehow, it's a page fault. The student shows up and it's a chair fault, right? So there is no chair. And so I will create I literally like my what is it? My TAs, they look at it's actually kind of hard. There is no map of the room in Utah, right? At my previous institution, we had a map. So that's why we screwed up, and the last row doesn't have those 3 extra seats, right? So our algorithm screwed up, and we have to squeeze everything together in the last row, right? Last during the midterm. But so that's my view of the room. I say, look, I have the chairs. In the middle, there is an empty space. It's like bias, right? So we cannot use it. In a side, there's also some chairs which are used by bias. We know that we allocate good students in the front, right? So here, and bad ones in the last one, right? And so that's my read-only, like for good students, and read-write. Right? You got it? So it's a view. And of course, you say, what if I somehow messed up this kernel map and said that read-only region overlaps goes into the writable data part of the data section? And suddenly some of your writable global variables become read-only. And when you access them, trying to write them, you will get a page fault later. That's what will happen. Is it clear? Good. Okay, so we got it. So the loop conceptually is simple. If we have this function which does this walk page table directory, kind of the goal is also simple. We just will write into this, we'll write the physical address into this PT entry with permission bits and present bit, and it will increment both virtual address A and physical address PA by 1 page, right? So again, very simple code. Let's take a look at how we construct this walk page table directory, right? And that's my essentially like kind of like jumping forward, which I just explained. This line updates the page table directory entry with the physical address and permission bits, like essentially writing right here, right? So that's not super surprising. But this function is a little tricky, right? And I said, okay, let's think of how we're going to do it. So you figured it out. You said, let's walk the page table. Specifically, remember, this is how the page tables are constructed on Intel. So essentially, you take a linear address, you split it into 10 bits, higher 10 bits, which provide an index, those 10 bits here, which are coming from here, provide an index into this page table directory. And then the next level, the next 10 bits here will provide an index into this one, right? So, and that's exactly what this function walk page directory is doing, right? Again, I'm spending time because I will ask you to write a similar function as a homework, right? So let's just take a look at those details. So not surprising, you have a virtual address. The first thing you do, you say, give me the very first top 10 bits. I'm using this macro PDX. So PDX is specifically a macro which takes the virtual address and shifts it by 22, right? So this PDX shift is 22. saying that if the top addresses are just like, give me this top addresses. This and is not necessary. I was actually talking to the authors of the x86 to remove this. They refused because when you shift, those bits will be extended with zeros anyway, right? But if you have the second macro, which is give me the middle 10 bits, then this and becomes necessary because now you shift simply by 12, right? So the top 10 bits will be still there with some numbers, and that's why they make sure that you don't get them. You just like discard them with this mask, right? Is it clear? Okay, cool. So two helping macros. You say, look, we got the entry in a page table directory, right? So if it's the page table like this, so this page directory entry is a pointer which goes right to this entry, right? Agree with this? Okay, so we check whether the page table directory entry is present. So remember the present bit. So essentially we say, look, if this guy has a present bit set to 0, it means that there is no next level. At this point, what x86 is doing, it may choose to allocate the next level. So this function walk page directory will be called from multiple contexts later in x86. And this alloc flag decides whether this allocation should be done or not. In this specific case, we said, yes, we want to allocate. And so in this case, when this check fails and the page table next level is not present, we will allocate it with kalloc, which we just construct, getting the page from the free list of pages, right? Great, good.
I didn't follow at the mask bit part.
This mask bit part.
Yeah. What happened?
So imagine you have some address which goes like 11 something 111 000. You say I care about those 10 bits here.
Yeah.
You shift them by PTX shift, which is 12, right? So the number which you get, those bits will be discarded, right? And you will have something like 000, but then you still will have those bits 11 111 011, right? So for example, right? You only need these 10. So you have to discard these bits, right? These 10 bits. That's why you mask saying only give me the lower bits. This is the mask. F expands into 4 bits, right? Yeah. So you have 2 Fs. So you expand it into 8 bits and 3 expands into another 2, right? You masking the lowest 10 bits, saying that everything else will be 0 anyway, right? So, agree?
And one, you said you told that you suggested to remove the first mask.
Right.
Why did you use?
Because why? I don't know, like this, just, I can send you an email at some point, what I got from them. There is no reason for this mask, unless maybe on some architecture, and I forgot, they didn't provide this answer, but I'm just guessing that maybe, but no, I think it's a C standard. So this shift always expands to zeros, right? Unless I'm wrong. Like the top bits will be zeros. It's not like a rotating shift or anything like that, right? Do you know? I think in C it's always just expands.
No, it's the C standard.
Right, I think so too. So that line was also like a little confusing, and I was trying to remove it to make sure that it's cleaner for students. Okay, so we back to this page, allocated the second level, right? So if it didn't exist, we just allocated it, right? So specifically this one, right? We said, okay, this one entry was there, the present was not set, we allocated this one. Agree with this? Okay, so that's good. And in case it was already allocated, right? We essentially say, okay, we got it. So we will get, what we need to do is really, we extracting the address of this page table level, right? From this entry. Remember, there is like a slight, there will be, it's not just the address, because the address itself is only 20 bits, but there will be also some flags, right? That's why we're using a couple of things here. So this is the line, which is used in code, right? It uses a couple of macros. The first macro just extracts the bits of of the physical address itself, right? That's very easy, right? You just mask the rest. However, there is a second macro here, which is P2V, right? Because really what you're doing here, this page directory entry, right? An entry in in a page table, right? Let me just let me go here to explain this argument. So it's a little bit of trickery here. We got this yellow entry, right? We have the value of it, right? Remember, the top 20 bits will provide us the physical address of the second level, right? However, we can't really use the physical address. Agree with that, because we cannot load it in register and say use physical address. We really need to convert this physical address. Maybe this page is sitting somewhere over here, right? We got the physical address, but we really need to convert to a virtual address, which we can really use in a register, right? So how do we do it? I said there is this P2V, physical to virtual address macro, but what's inside that macro? Knowing the physical address of a page, how can you convert to a virtual address of this page in x86?
Does it do like another page? Well,
Yeah, can you walk it backwards? Like a couple of assumptions about how we constructed the address space are critical here. So it's a very easy answer. Just take a look at this picture or this figure. There's a page. It sits here. Let's say we gave it to the free memory allocator, right? We know the physical address of this page. Exactly. We just shifted by 2 gigs. And that's why this construction is important, right? Because if we haven't done it and didn't do this, we wouldn't be able to locate this address, right? So, but we know how it can be done. So is it clear that we know that we just shifted? We mapped all the available physical memory in a system. Like any physical page which we can access will be mapped here, right? And we simply shift by 2, converting between the physical and virtual, right? It's only in the kernel. In the user space, it cannot be done because the pages will be mapped randomly, right? So we'll take a look. But the kernel is very, very careful, right? And we did it this way, right? Agree? Is it clear to everyone? Okay, so this P2V macro is not super hard. So page address macro just masks the bits. This P2V I just explained. So if we have a page here, right? So any of those pages from 0 to fistop will be mapped here from 2 gigabytes to 2 gigabytes plus fistop. And you suddenly having an address which is here, somehow there is a bug in your kernel, which there shouldn't be a bug, but imagine there is a bug. If you shift by 2, it can land you somewhere, who knows where, and that's a bug, and you will crash miserably, right? Just make sure that you don't make this bug. Okay, cool. So we have this. So P2V really just cool. Eraser. Oh, okay. So V2P, virtual to physical, subtracts the kernel base, which is 2 gigabytes, and P2V just adds back 2 gigabytes. So you can always convert this way. Okay, cool. So at this point, we say, look, we got it. So we did this macros, like first get the bits of physical address, then convert it back to virtual address. We have this pointer page table. It's a pointer to the second level of a page table, and we are ready to return it, right? Agree? Here is my tricky poll question again. What is that we're returning? Like, take a look here again. This line, right? Page table, an address. A little tricky. Maybe I should. And I'm asking, like, what is that we're returning here? Let me enable it on the poll. Let me log this activity and go back. Lots of polls today. Activate. Cool. Unlock. Do you see it? Yeah. Which slide you think is most helpful? This one is good enough to correctly. Now it's a democracy in the age of social media. So the answers are uniformly split. I do this. Yeah. Let me just do it. And remember, again, think about it at a high level. So what was the goal? What is it we wanted to return from this function? I can. So do we understand what this ampersand means? VREF? It's an address. It takes the address of what? Of the entry in this array, right? So if we have it here, which array and which entry we're talking about? Who can tell me the number? 3? Right, 3. You're right. Everyone agrees that it's 3? Yeah, success, right? Anyone? Okay, let's ask. Let me show what we have on the poll. So on the poll we have. If I do present, so wait, still presenting this one, whatever returning, right? So most people are correct on 3, right? So some people are fixing the addresses, right? So fixing the answers, but mostly we are converging, right? Originally it was less uniform. So okay, good. Done with the poll. Everyone is done in the class. Good. Deactivate. Oh, it's already locked. Oh no, it's different one. What is this nonsense? Like it's different activities. What are we returning? This is the one which is active. No chances for you. I don't know. Activate, present. Okay, whatever. Not sure. Okay, so we are almost there. We only have like 4 minutes. So we really return the address of this entry, right? So, and that's not super hard. So because we took this ampersand, p table was this all array, and we said something p, I forgot the exact syntax here, ptx of a virtual address takes this 10 bits, right? And we're specifically returning the address of this entry. Is that clear, right? Cool. So, okay, so at this point we say, okay, we walk the page table, we're back to this map pages function, like we got the address of the PT entry, and I already said that, okay, so sure, if it's suddenly already allocated, it says, okay, there is something wrong with the kernel map, let's panic. At this point, there's no meaningful way to move forward. It's an unrecoverable error in the x86. It's kind of like an assert, which is put in C or C++. They just do the check here.
Sorry, it's probably just semantics, but why call it walk page directory when it's ultimately an entry?
No, because the function takes a virtual address A and walks the page table directory, essentially says, and returns the entry which maps this, which is responsive. Like, okay, so maybe a better name would be something like get PTE or something, like right?
Traverse.
Right, or walk and get PTE or something, right? No, you're right. So naming may be a little awkward, but.
How do you mean page parallel and panel?
No, it says that you trying to map this entry twice. If you've seen this entry, the bit is present, it means that you already walked it. So it means that there is a bug in you and you're trying to map this page table one more time. They don't want to do it. Okay, and here just update the PT with a physical address, as I was saying before, increment everything by a page size. At this point, you say, okay, this kpage directory is this new page table, which we wanted to construct from the beginning, and we actually constructed it. So we have now a pointer to it, and now we run this switch kvm function, and a switch kvm function says, okay, get it. So I have a helping function which will load CR3. You take this address, but this is a virtual address, so use this V2P conversion back again to say that convert from virtual to physical, and at this point, you have a new page table. So this page table, the boot time page table is gone. It's still allocated. We didn't do anything to it. It's just no longer used. But we use a new page table, which we constructed today. It sits in your CR3 register at this point. And at this point, we can move on with finishing initialization of the kernel. We still have to do maybe the segmentation and like redo the global descriptor table, initialize interrupts, and then we are ready to create a new process, right? And so this is what we're gonna do next week. So question.
So like, it seems like the like shifting back and be like really error prone. Is that why you chose to like in like your implementation to not have it, like to not map
Right.
the physical like
Right. So the question is like I keep mentioning that in my new kernel, I map the physical memory 1-to-1. When we build this mathematical proof, it's a little easier. It's almost the same to shift back and forth, but it complicates the proof. But and as you say, it's easier. If it's easier for the proof, it's only easier for the proof than it's correct, which is it usually means it's easier for the human as well, right? So. Right, right. But we can talk about it towards the end that really not every kernel maps all available physical memory. Why? Because first of all, it's usually not needed. And there were windows of time when the physical memory was larger than virtual memory, believe it or not. On the 32-bit machines, there is this extended mode which says, look, you only have 4 gigs of virtual addresses, but really machines were shipped with more physical memory at this point, and you were selectively mapping and unmapping memory. So right now we're back to the case when the virtual address space is large, 64 bits, physical space is large as well. So it's a design choice, but typically mapping all the pages is not necessary. Just x86 does it for simplicity, but Linux will not. But we can come back to it as well. Okay, so I will see you next week. Okay, one question. So among the people in the room, since you have a power to vote, who needs an extension on a homework? Okay, enough people. So I will give an extension until, let's say, Sunday night. Is it okay? Okay, cool. Then, and then I'll assign the new ones. My website is down. No, I didn't. Yes.